Okay, so now let's get on to chemical reactions. Now, this is essentially, we are going to take different atoms, compounds, we're going to mix things up. We're going to start using our knowledge to predict what is going to be created. Now, in lesson 13, your objectives are identify formation and decomposition reactions. And you're going to, once you identify them, you're going to want to predict and write them. Basically, we're looking at these right here, and we're not going to get into that just yet. But this is a very important step, and believe me, we've just finished doing all of the molar mass and the moles and all those calculations. Well, when it comes to chemistry 20, for example, the ability to do equations and predict them and then do the math is fundamentally crucial. So everything we've just done, the moles, the molar mass, crucial. What we're doing now is how to write reactions properly. In Chem 20, all the calculations and all of this formula building, predicting, all comes together. Extremely important. There's one thing I'd like you to do right now. You may have to pause this, but you need to have your periodic table with you right now. Throughout this unit so far, you've been hearing how I've been saying I've been doing things wrong, and that's okay. There has been something I've been ignoring until this point, and we won't do it any longer. It is called diatomic atoms. Now, if you have your periodic table, you could feel free to make little jot twos in there. And I'll tell you what I mean here in a second. So certain atoms exist in nature in pairs. So for example, hydrogen. Hydrogen is up there, number 1. So if you want, so here's H, and it has 1. You could put a little 2 there. Or if you want, you could put a star somewhere. The other ones that are diatomic, okay, are nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So somehow I would mark for yourself, make a mark for they are diatomic. Now, what does diatomic mean? Diatomic means they are found in twos. So if you're doing an equation, and let's say you have, let's go sodium plus, if someone said it's sodium plus chlorine, you don't just put Cl. It must be Cl2. Chlorine is diatomic, which means it always has a 2 with it. Again, if it was Na plus bromine, you wouldn't just put Br, you would have to put Br2. This does not change any of the rules we've been following so far. It just means it's one more step you have to remember. Here's another one. Mg plus magnesium plus iodine. Well, iodine is diatomic, which means it has to be written as a 2. So the rule is, when these are by themselves in a formula, they must be diatomic. So I would recommend that you do put that on your periodic table somehow for you to remember that. Another exception that you might want to put here, if you find phosphorus, which is the P there, phosphorus exists naturally in a state of 4. So if you were to write phosphorus by itself, it would be P4. The other one that we worry about is sulfur. Sulfur exists in a state of 8, so it would be S8. So those are just your examples. Now, because I'm moving into how to write formulas, I just want you to know that when these are by themselves, some of them have a 2 with them all the time. One of them has a 4, and one of them has an 8. That is crucial moving forward, that when you write them by themselves, they have the right value with them. All right, formation reactions. Well, what does formation mean? Formation to me means building or put together. There is a simple way of doing this. Some people like to call this, they say A plus B. And typically speaking, we're going to have, this will be a metal, and this will be a non-metal. And they are going to bond, and we're going to end up with a compound. And that's going to be AB bonded together. Very straightforward. It might help using this AB notation because sometimes it helps keep track of where everything goes. Again, keep in mind some of these will be diatomics and so on and so forth. But it's not difficult. It's just a matter of balancing your equations again. So if you're looking for the page number in the textbook, this is page 91. Let's move on to some examples. All right. Actually, I'm just going to go back for 1 second. You notice here I put metal, non-metal. In most cases it is. It could be a non-metal, not a big deal, but I just want you to know it's typically you take something A plus B and it becomes AB. All right, let's go back to the examples. I apologize. All right, let's take something like calcium reacts with chlorine. So let's do it. So you have calcium plus chlorine equals something. Now, I hope that you realize that chlorine is one of those diatomics that you had on your periodic table. We just talked about that. So you must put a little subscript 2 right there. Now, this might also help you. I put this as A and I put this as B. Well, in a formation reaction, A and B come together. So it's going to be CaCl something. But what's going to happen here? So, does everyone remember? Let's look at the charges here. The charge of calcium is 2+. The charge of chlorine is 1-. Which one do we need 2 of, guys? 2 of the chlorine. Okay, and I'm sorry for this A looking so bad. Okay, we've put that together. We took our A, we took our B, we put them together, but what did we have to account for? Must account for correct charges. This was an ionic bond. We could even name this. That would be calcium chloride. Okay, we can try another one. There really is no end to this. We could go on for. Let's try nickel 3 reacts with, that's the with symbol, with oxygen gas. We haven't talked about the states yet, but we'll get there. So we have nickel plus oxygen. Now, oxygen is one of the diatomics, so you got to put a 2 right there. The charge of nickel, we put 3, so we're looking at 3+. Oxygen is 2-. I hope by now you see this is the lowest common denominator method. So that means we must have, okay, so we have nickel 2. Now, we have a little bit of an issue here. We're going to put oxygen right there. Now, if you look at this, based on the lowest common denominator method, we have to have 3 oxygens. But, actually, no, it's not much of an issue at all. We're just going to put right here 3. Sorry, everybody, I kind of messed it up. My point to you is, if you follow along with my logic there before I started confusing things, the lowest common denominator method, this was a 3, this was a 2, it goes to 6, so times 2 times 3, that's where the 3 comes from. I'm sorry. So in this case, this is a molecular compound. If you wanted to name it, it would be dinitrogen, okay? And hopefully you can go from there, trioxide. Now, if you're really experienced with chemistry, you're going to say something, things are not balanced. And maybe that means something to you, maybe it doesn't, but believe me, we are getting there. My whole point right now is knowing how to put A plus B, balancing your charges. And wow, did I just blow this? That's Ni, not nitrogen. That's Ni2, guys, sorry. That should be nickel. That's going to change everything. Nickel oxide. Well, despite my mistakes there, I hope you still follow along with this. It's still an ionic compound. All right, let's move on to another one. We can do one last one if you want here. Hopefully I won't mess this one up. Let's go with, let's go titanium. Titanium has three, let's go with 3 again. Titanium reacts with, oh, I don't know. Let's go sulfur. Okay, so it's going to be Ti, that's a 3 plus sulfur. Now, what's the deal with sulfur, everybody? Sulfur, when it's by itself, has an 8 with it. And the charge of sulfur is 2 minus. So we have TiS. This is lowest common denominator again. We're going to need 2 of those and 3 of these. So your final compound is titanium sulfide. Hopefully this is becoming a little bit more clear for you now. Fairly straightforward and simple. You just got to get those balances together. This is ionic bonding. Okay, now we can change gears a little bit. Decomposition is just the opposite. Decompose, in my mind, means break down. In terms of the simple letters, this is where you start with AB. You start with a compound, and they break apart into A and B, which are elements. Okay, so we'll give some examples a try. Let's go with, I mean, we can try anything here that we want. Nothing here is too difficult. Let's try MgCl2. Well, that's going to be your AB. That's your compound. It's going to break apart into its 2 elements, Mg plus Cl. Now remember, chlorine's by itself has to have a 2, A and B. Nice and easy. Another one, we'll go with calcium oxide. So that's your AB, that's your compound, and it's going to split into an A and B, which are your elements. It should work out to be calcium and oxygen, and this should have a 2 with it because it is diatomic. One final example here, I suppose. Let's try magnesium sulfide. That's your AB, your compound. It'll break into A plus B, which are your elements. So this should be magnesium. This should be sulfur. Now sulfur is by itself, everybody, so that should get an 8 right there. I hope that you find formation and decomposition reactions fairly straightforward. It's all about accounting for, make sure that you have the correct charges balanced, like ionic compounds. Finally, make sure that you've paid attention to the diatomics, the things that have 2s when they're by themselves, and the phosphorus has a 4 and the sulfur has an 8. That is crucially important, because if you don't remember that, you're going to have a hard time creating the right compound. Anyway, I will give you guys some practice with these skills.